Let's talk about solving an equation like this. X to the 6 plus 7x cubed minus 8 equal to 0. And the first thing to recognize is it has the look of a quadratic equation, except not the right powers, right? To be quadratic, it has to be like x squared plus 7x minus equal to 0 or something, where the powers are the second power and the first power and nothing else. So you can either just factor this as is, or you can do a u-substitution, where you say, okay, I'm going to pick u to equal, do I want to pick x cubed or x to the 6th? Well, if you pick the wrong thing, it's going to be really obvious. If you pick u equal to x to the 6th, which is the wrong thing, then u squared will be x to the 6th squared, which is x to the 12th. And I don't have an x to the 12th. So you always want to pick u to be the thing that is the power that's, I don't want to say smaller because if it's negative, it's not really true. The power that's closer to 0. So I'm going to pick u equal to x to the 3rd power. And then u squared will be x cubed squared, which is x to the 3 times 2, which is x to the 6. And then we can start replacing things. Okay, that's going to be u squared plus 7u minus 8 equals 0. And then we can factor this. Or if we didn't factor, we could use the quadratic formula, which would be kind of annoying, but it's an option. So this factors as u minus 1 times u plus 8 equal to 0. And then from this factor, we get u equal to 1. From this factor, we get u equal to negative 8. But then we have to actually solve for x. So u is equal to x cubed. So that means we have x cubed equal to 1. So x is equal to the cube root of 1, which is 1. And x cubed equal to negative 8, which means x equals the cube root of negative 8. And the cube root of negative 8 is negative 2. So those are our solutions, positive 1 and negative 2. And we only get 2 solutions here, even though it's a 6th degree equation. Sometimes you get way less solutions than the degree. I will mention, not that it's important, there are 4 other solutions. They're just imaginary or complex, and we don't bother with this. But technically, every kind of polynomial equation has as many solutions as its power. Sometimes some of them are complex, sometimes some of them are repeated. We're not going to worry about the complex ones. We're just going to worry about the real ones. The other way you could have done this is just by factoring it as x cubed minus 1 times x cubed plus 8. That would also work just fine, right? This multiplies out to x to the 6th. You get a minus x cubed, you get a plus 8x cubed, and then you get a minus 8. And then you would see the same solutions, right? You're going to get x cubed equal to 1, which is literally just taking you right to there, and x cubed equal to negative 8, which is really what we have right there. So you don't, what I'm trying to say is you don't have to do this u-substitution process, but some people find it much easier to do it that way. But if you can just factor it by seeing it, then that's also perfectly good. So let's look at the next one. So first of all, before I do anything, I should bring everything to one side. So I'm going to write it as x minus 7 root x plus 12 equals 0. And you typically want to write these always so that the powers of x are descending in power from highest to lowest. So this is really, I'm going to rewrite this as x to the 1st minus 7 times x to the 1/2 plus 12 equal to 0. And now hopefully it's a little more obvious that, oh yeah, these are in descending power. So I want to pick u equal to the x thing that's closest to 0. I should say the power of x that's closest to 0. So I'm choosing u equal to x to the 1/2. Really, I'm just trying to pick the thing so that when I square it, I get the other thing, right? That means u squared is going to be x to the 1/2 squared, which is x to the 1. So great. Those are the things I have. That's what I want. So I'm just going to rewrite this as u squared minus 7u plus 12 equal to 0. And a lot of these factor because we're not trying to make the problems impossible. So this is going to factor as u minus 4 times u minus 3 equal to 0. So then I'm going to end up getting u equal to positive 4, u equal to positive 3. But u is really x to the 1/2, or if you prefer, the square root of x. So really I have x to the 1/2 equal to 4, which means x is going to equal 4 squared, which is 16. And here I get, I'm going to write it differently this way. I'm going to say, instead of writing x to the 1/2, I'm going to say it's the square root of x equals 3, so x equals 9. And those are my solutions. Yeah. There is, so I will mention, because you might have seen this in Math D, another way of solving this equation would be to square both sides. Right? You could totally, not that we're really going to cover that, but you could square both sides, x plus 12 quantity squared equal to 7 times root x quantity squared. And then this would be x squared plus 24x plus 144 equal to 49x. That's another way you could do this. It's not what I would prefer to do in this particular, because it's not really the point. What I want to say is, you might have learned when you did this, that when you square both sides of an equation, you introduce the possibility of what's called an extraneous solution. Meaning you might have something that's a solution to this that wasn't actually a solution to your original equation. That doesn't happen in this problem, right? If you plug back in our solutions, 16 and 9, they actually are solutions. 16 plus 12 is 28, and 7 times the square root of 16 is also 28. And 9 plus 12 is 21, and 7 times the square root of 9 is also 21. But if we had gotten like a negative answer, it might, or I should say, like if you had somehow gotten something that wasn't the answer, like -4, that's when there's a problem. So we will see another example a little later on where the answers you get actually aren't answers to your original question. And it really has to do with the fact that right here, you're raising both sides of this to an even power. When you square both sides, or you raise both sides to the 4th power or to the 2/3 power, if you're doing some sort of squaring, you often have to check for extraneous solutions. It's not a huge deal. It's not a big theme in this class, but it is something to be aware of. Let's look at a couple more examples. I want to solve, what do I want to solve here? I want to solve 2x to the -2/3 plus 5x to the -1/3 minus 3 equal to 0. Okay, so here is where the thing I was saying about letting u equal the x to the power that's closer to 0 is going to be meaningful. Right? Because if you pick the smaller number, -2/3 is more negative than -1/3, and so it's technically the smaller number. I want the number that's closer to 0 though. So I'm going to pick u equal to x to the -1/3. And then I'm going to check u squared should be the other power of x, and it is. X to the -1/3 squared is just x to the -1/3 times 2, which is the -2/3 power. So great. This is going to become 2u squared plus 5u minus 3 equal to 0. And I'm going to solve this using the, whatever you want to call it, the multiply the thing and the add it to the thing method. So I know I want to multiply to 2 times -3, which is -6, and add up to 5. So I want to be 6 plus -1. So that's going to multiply to -6 and add up to 5. So I'm going to rewrite. I saw someone do something kind of cool. I don't really know how to explain it, but I saw someone on their homework, which I've almost finished grading, not quite done. But one of you was doing something that I thought was, I'm sure you must have learned it somewhere. It was neat. You were doing this thing, so you had like, I honestly am terrible at this part. You multiply to -6, you add it to 5. You wanted you added, no, that's right, yeah. And you want a 6 and a -1. And then you did this thing where you divided everything by the leading coefficients. So you divided this by 2 and divided this by 2. And then your answers were like 3 and -1/2. And that was super cool. And I don't really know how, where that comes from, but it totally works. I'm going to do it the way I usually do it, but I just want to point out there are other ways to do this. And if you're doing something that works for you and it works, that is fine. But yeah, it was neat. Good job, whoever that was. So I'm going to write this as 2u squared minus 1u plus 6u minus 3 equals 0. And then we're going to do the factoring by grouping. From here, I can factor out a u, I'm left with a 2u minus 1. I feel like I might be making a mistake. No, I don't think so. I'm always worried I'm making a mistake. No, it looks all right. Okay. And then from here, I'm going to factor out a 3. I'm left with a 2u minus 1. So then we have 2u minus 1 times u plus 3. 0. So those are the numbers you put like. You'd have a u plus 3, and you'd have a u minus 1/2, except it's the 2u minus 1, 2 multiplied by 2. Yeah. Whoever was doing that was like, all right, cool. And then we would say u equals -3 and u equals +1/2. And then we have to go back and find out what x is. So if u equals -3, we're going to replace u with x to the -1/3. So x to the -1/3 equals -3. And then I know I didn't really say this for the previous one, but to undo a fractional power, to undo any power, you're going to do the reciprocal power. So what I really should have said is, over here when we were solving this, what we really did was when we had x to the 1/2 equal to 4, we raised both sides to the power that's the reciprocal of 1/2, which is 2. Because 1/2 times 2, right? Power to the power, you multiply the powers. Sorry, my phone is making noise. 1/2 times 2 gives you a power of 1, and x to the 1 is just x. So that's the whole idea. If you're ever trying to solve for x to a power, you're just going to raise both sides to the reciprocal power. So I'm going to raise both sides here to the -3rd power. Because -1/3 times -3 is +1. So on the left, I'm going to get x to the 1st, which is just x. On the right, -3 to the -3rd is 1 over -3 to the +3rd. And -3 cubed is -27. So that's going to be -1 over 27. You could write 1 over -27, but typically if you have a negative in the fraction, you either write it on top or in front, but not in the bottom. So like it'd be okay to write -1 over 27 or -1 over 27. But 1 over -27 is never the way we write it for some bizarre reason. Not really any good reason, just like that. Same idea here. F x to the -1/3 equals 1/2. So we get x equal to 1/2 to the -3rd. And then I would probably rewrite that as that's going to be 2 to the +3rd. Right, it's 1/2 to the -1 to the 3rd, and 1/2 to the -1 is 2. And then 2 to the 3rd is just 8. So those are my answers here. Okay, I got one. Let's look at 2 more examples of this, and then we'll start talking about graphing lines. Graphing lines is like, it'll be super fun. Well, they're not fun. It'll be easy. I'll try and give you the best, most efficient method for graphing lines. So this next problem is going to be slightly disappointing in that there's not going to be any solutions. That's okay. Sometimes you get no solutions. So x plus 3 times the square root of x equals -2. So let's go ahead and write this as x plus 3 times x to the 1/2 plus 2 equals 0. All right. And then let's go ahead and do the usual thing. We're going to let u equal x to the 1/2. And then u squared will be x to the 1/2 squared, which is x to the 1, which is just x. So we're going to rewrite this as u squared plus 3u plus 2 equal to 0. So then factoring this, it factors as u plus 2 times u plus 1 equal to 0. And so now we're going to get u equal to -2 and u equal to -1. And now here's where we need to kind of really be observant. If I go ahead and try and solve for x, I'm going to have x to the 1/2 equal to -2, and x to the 1/2 equal to -1. Now, there's a couple ways to see this isn't going to be right. One way is to actually write it as a square root. But if you write it x to the 1/2 as the square root of x, you might remind yourself, oh, when you take a square root of a number, it never comes out negative. Right? So there's no real number whose square root is equal to -2. I know you might say the answer is 4, and I would tell you, no, the square root of 4 is +2. We never let it be the -2. So there really isn't a solution to this, but let's pretend like we weren't paying attention. Let's just say we square both sides because we wanted it to work. So we have x to the 1/2 squared is going to be x equals -2 squared, which is 4. And the same idea here. Even though really you can't have the square root of x equal to -1, if we weren't paying attention, we would get x equal to -1 squared, which is +1. But now I want to point out this isn't a solution. Because if you plug it back in, let's say you plug it back in here. Or either way. 4 plus 3 times the square root of 4. Well, 4 is positive. The square root of 4 is 2. That's also positive. 4 plus 3 times a positive number is going to be a positive, not a negative number. So the problem is when we plug in 4 here, we need the square root of 4 to be -2 so that it comes out to be equal to -2, but it's not. The square root of 4 is equal to +2. So 4 isn't a solution because 4 plus 3 times the square root of 4 is equal to 4 plus 3 times 2, which is 4 plus 6, which is 10, which is not -2. And the same thing is true if we plug in 1. If you try plugging in 1 plus 3 times the square root of 1 is equal to 1 plus 3, which is not equal to -2. So I don't think anything really comes up like this in the homework, but I just want you to be aware when you do a quadratic u-substitution like this, if at the end you're squaring both sides to solve for x or raising both sides to an even power, your answers might not actually be answers. They might be extraneous answers. So in this problem, I would finish it by saying there are no solutions. Which always feels disappointing. Like, no solutions. Really? We did all that work for nothing? Okay. Let's look at one more example. This one's going to be a little bit strange. Not that strange, actually. Sure. Let's look at something like, yeah, that's kind of the easiest. So let's do x to the 6th plus 2x cubed minus 4. So here we have another thing, the quad. In fact, I should ask you guys, what should I let u equal? You should be x to what power? X to the 3rd or x to the 6th? Yeah, it's good. Excellent. I like the thing. Exactly, x to the 3rd. So that means u squared will be x to the 6th. And so then we're going to write this as u squared plus 2u minus 4 equal to 0. And as you might recognize, this ain't going to factor, right? There's no way we can multiply the -4 and add up to +2. It doesn't work. So instead, we'd have to use the quadratic formula. So we would get u equal to -2 plus or minus the square root of 2 squared minus 4 times 1 times -4 all over 2 times 1. And then we would get -2 plus or minus the square root of 4, and then -4 times 1 times -4 is +16, so 4 plus 16 is 20 divided by 2. And the square root of 20 is the square root of 4 times 5, and the square root of 4 is 2. So I can write this as -2 plus or minus 2 times the square root of 5 over 2. And then I can divide each part by 2 and get -1 plus or minus the square root of 5. Okay, but that's what u is equal to. So if I want to solve for x, that means I have to say x cubed is equal to -1 plus or minus the square root of 5, which means x is going to be the cube root of -1 plus or minus the square root of 5. So we get two different answers. We get the cube root of -1 plus the square root of 5, and we get the cube root of -1 minus the square root of 5, which is just feels kind of weird, right? Like, I don't think there's any homework problems where you really have to do that, but I just wanted to point out that it is possible that you might have to use the quadratic formula and get some irrational answer, and then you'll have to modify it by what x is actually equal to. It's kind of interesting. I should also mention both of these answers are real numbers. -1 plus the square root of 5 is some positive number, and we can take the cube root of that. -1 minus the square root of 5 is some negative number, but you can also take the cube root of a negative number. Odd roots, 5th root, 7th root, cube root, 9th root, 121st root. You can always take the odd root of any positive or negative number and get a real response, a real answer. So that's how this quadratic u-substitution stuff works. And again, the only time you really ever use it is if you have a trinomial, meaning there's 3 terms, and one of them is constant, one of them is x to a power, and one of them is x to twice that power. But you can't do this if you have anything else. So if you had something like, I don't know, I don't even want to make something up because it'll just look funky. So that's what you're looking for. X to a power, x to twice that power, and a constant term. How did I only get -1 plus or minus the square root of 5? I'm not sure what that question is exactly trying to get at. I'm guessing what the question is trying to get at is why I divided each of those parts by 2. I think that's what you're asking. And that's because when you have a fraction, right, when you add or subtract things together, you have to divide each of them by the denominator. So this is really -2 divided by 2 plus or minus 2 root 5 divided by 2. And then the -2 over 2 is -1, and 2 over 2 is 1 times root 5. If that's not addressing what your question is really about, let me know and I'll try and get there. But I think that's what you're asking. And so then our actual answer, right, was the cube root of that thing. So it's the cube root of -1 plus root 5 and the cube root of -1 minus root 5. Yeah. Yeah, and I will point out, I know I didn't finish reading you guys' homework quite yet, but I will point out a few of you did make this kind of mistake on the homework where you only divided one of these pieces by the 2. So like I saw a few people will say like the answer to this incorrectly, they said it was like -1 plus or minus 2 root 5 because they didn't divide the second thing by the 2. So just be aware some of you made that mistake and try not to make it in the future. Okay. So then graphing lines. So here's what I want to say about graphing lines first and foremost. What I would encourage everyone to do when they graph a line. Sorry, someone asked a question that I should respond to. Is it the same for negative exponents? I'm not sure is what the same. I'm not exactly sure what the like you mean like when we do this thing?
Yeah.
Yeah. So yeah. So for example, yeah, that's because we didn't do a lot of negative exponent examples. But if you had something like, I'm going to make something up that's going to be, I don't know. Sure. The problem is for the number.
There's a problem on the homework with negative exponents.
One more time, sorry.
There's a problem on the homework with negative exponents if you want that one.
Let me give you an example. Let's say we had something like x to the negative second. Let's see, I'm just trying to make sure this doesn't turn out too terrible. It's just fun. Minus x, minus 3x to the negative first, minus 4. Sure, yeah, that's fine. Let's see if it's something like that. then the process is very similar, yes. You would let u equal x to the -1, and then u squared would be x to the -1 squared, which is x to the -2. And then we rewrite this as u squared minus 3u minus 4 equal to 0. This one we can factor. So it's going to be u minus 4 times u plus 1 equal to 0. So our u solutions, which are not our final solutions, are u equal to 4 and u equal to -1. And then solving for x, so we have x to the -1 equal to 4 and x to the -1 equal to -1. So then we're going to solve for x by raising both sides to the reciprocal power. The reciprocal of -1 is -1. So we're just going to raise both sides to the -1 power. So x to the -1 to the -1 equals 4 to the -1. X to the -1 to the -1 is just x to the first, which is x. And 4 to the -1, I would prefer to write as 1/4. Same idea here. X to the -1 to the -1 equals -1 to the -1. X to the -1 to the -1 is just x. And -1 to the -1 is 1 over -1. But 1 divided by -1 is just -1. So yeah, that's how you deal with the negative powers, just end up giving you a reciprocal at the end. So like, yeah, and if it was like x to the -2, then you would solve it by raising both sides to the -1/2 power. But yes, you always use the reciprocal power, and if your power is a negative, the reciprocal is also going to be a negative. Good question. I'm glad you asked that. Okay. So the deal with lines is if you're asked to graph a line, in my opinion, you should really graph it by plotting two very specific points. I think whenever you graph a line, you should plot the x-intercept and the y-intercept. The only exception, of course, is if you have a horizontal line or a vertical line, because those don't have both an x and a y-intercept. But any line that is not horizontal or vertical, those are the 2 points you really should plot. So a couple things about lines. There are really 3 forms, but there's 2 forms we're going to talk about. So there are 2 forms. There's the form I imagine most of you are familiar with, which is the y equals mx plus b form. And the y equals mx plus b form gives us some information. That's why we like this form. The m is the slope of the line, and the b is the y-intercept. So we really like this, what's called the slope-intercept form, because it tells us a lot of information. But there's also what's called the standard or general. I think it's called the standard form. People use words that kind of made up. So ax plus by equals c. And this is what's called the, I want to say it's the general, I think it's the same form. It doesn't really matter is what I should say. This is nice for some reasons in that you can cut, there's a standardized way of writing it, but it's not so nice because it doesn't give you as much information. What we're going to see is that whether you're given an equation like this or an equation like this, it's super easy to graph it if you follow the same kind of recipe every time. So I want to graph y equal to -4x plus 12. And while you could plot many points, you don't have to, and really you shouldn't. So if you know something's a line, and you're going to know it's a line if you see you have y to the first and x to the first and no other powers of x. So it's a linear equation. So the graph is going to be a line if you see it's a linear equation. And once you know something's a line, you only need 2 points. You don't have to find the third point to make sure they're all on the same line. You only need 2 points. So I'm going to find the 2 points that someone's probably going to ask me to find anyway. I'm going to find the y-intercept. Do I have enough room here? Yeah, sure, I have enough room. So the y-intercept is a point on the y-axis. And if I'm on the y-axis, it should be noted that my x value has to be 0. Right? If I'm somewhere on the y-axis, I haven't gone left or right. I've only gone up or down. So to find the y-intercept, we start by setting x equal to 0. And I should mention, this is true regardless of what kind of thing you're graphing, whether it's a line, a parabola, a whatever, right? You always find the y-intercept by setting x equal to 0, because that's going to be not moving left or right. So let's see, if I set x equal to 0, I'm going to get y equal to -4 times 0 plus 12, which is just 12. So the y-intercept is 12. So my point is 0, 12. There's my y-intercept. And the same sort of process is true to find the x-intercept. Find the x-intercept. Well, now we're saying we want to find the point on the x-axis. So set y equal to 0, right? So on the x-axis, I've moved horizontally, but not up or down. So then I'm going to set y equal to 0. So I'm going to have 0 equal to -4x plus 12. And then I'm going to solve this. I'm going to add 4x to both sides. 4x equals 12. I'm going to divide both sides by 4. X equals 12 over 4 is 3. So my x-intercept is the point 3, 0. And then we graph it. Now here's the thing. I don't feel like you need to make a bunch of marks, meaning you don't need to go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, and 1, right? You don't need to do that. You just need to be approximate. So I know I'm 12 up, I'm 3 to the right. So I'm going to make my point 0, 12 about there, my point 3, 0 about there. And then I'm going to draw the line through them. Here's a really good reason for not making a bunch of marks. If you miss, it's really easy to fix. So that's what I would recommend doing. Only plot the points that are the intercepts, because those are the only ones that really matter. Yeah, there's a lot of other points on this line that you could plug. You could say, okay, here there's the point when x is 1, and if x is 1, y would be -4 plus 12, which is 8. That you could point out that, but nobody needs that. I don't want that. You don't need that. But yeah, I know it's. I mean, there certainly, I will say there are times when it is useful to be more precise with your graph. To draw like a bunch of like, hash marks for the integers for the x and the y axis, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and be more detailed. For a line, nobody wants that level of detail from you. All they want is to make sure that it is a line and you know how to draw it and what intercepts. And most of the time, when you're graphing things, there are some exceptions, but most of the time when you're graphing anything in math, people are going to ask you to plot the intercepts. All the x-intercepts and the one y-intercept that we typically get, if there is one. And so if you're already going to be asked to find the intercepts and you only need 2 points to graph a line anyway, you might as well just find those 2 and no other ones. None of this going over 1 and down 4, right? I don't need to use the slope in that way. You can, but I don't think it's very efficient. You know me, I'm all about the efficiency of trying to do it the fastest, easiest, best way possible. So you can certainly graph your lines in a different way, but I would really, really, really encourage all of you to try and do it this way. Find your y-intercept, find your x-intercept, draw the line through them. That is it, end of story. So let's look at some more examples. I want to graph the line y equal to 3x minus 5. Now, the nice thing about it being in the slope-intercept form is you can look at it and already see what the y-intercept is. The y-intercept is -5. Yes, you could also find it, right? You could set x equal to 0, and then you're going to get y equal to 3 times 0, which is 0 minus 5. I don't need you to write it as a coordinate pair, but you certainly could say, oh yeah, it's 0, -5. Right? Y-intercepts, the x coordinate is always 0. That's why we're setting x equal to 0 to find the y-intercept. In the same sort of way, my x-intercept, I know is going to have a coordinate that's something, comma 0. It has to have a y coordinate of 0 to be on the x-axis. That's why I'm setting y equal to 0. So then I'm going to set y equal to 0. Finding the x-intercept is usually a little more work than finding the y-intercept. We have to actually solve for x. So I'm going to add 5 to both sides. 3x equals 5, and divide both sides by 3. So x is 5/3. And I really do recommend using a fraction, not a decimal, because that's a repeating decimal that never ends. It's 1.6666666 forever. Let's just write 5/3. And then we're going to draw it. -5 is certainly a larger in absolute value number than 5/3, right? 5 away from the origin versus 5/3 from the origin. So I'm going to try and draw my y-intercept further away from the origin than my x-intercept. So there's 0. I'm not even going to label them yet because I know I'm going to miss, right? I usually don't even draw these until I just draw a line. I'm like, okay, further down than over. Yeah. And that's 0, -5. And that's 5/3, 0. And I really should say, it's not much more exciting than that. There's really like, that's kind of it when it comes to graphing lines. You find the x-intercept, you find the y-intercept, usually in the other order, and then you plot them in your graph. Now, it is worth noting, you can go up 3. Yeah, so one thing you totally could do is you could from here say, okay, my slope is +3. So I'm totally going to go over 1 and up 3. So you could say, I'm going to go over 1, up 3. That's going to get me to the point. Now, again, my graph is not excellent, so it's not going to look perfect. But that's going to be the point, this is going to be a little more over. This is where you would want to make your graph more precise if you're going to go over 1 and up 3. So over 1, up 3. So my x value increased by 1, my y value increased by 3. So you could say, okay, James, I'm going to draw the line, through these 2 points. And that is perfectly fine, except when I ask you to graph a line, I'm going to expect that you give me the y-intercept and the x-intercept. So you're certainly welcome to give me more information, but you're just making more work for yourself if you do it that way. So again, it's okay to graph it that way, but I'm still expecting to see that x-intercept there. It's a fair point though. So yeah, you can do the up and over thing, but you still have to find the other intercept. So let's do one more than one more. How much time? Okay, yeah. So let's say I want to graph y. Actually, I'm going to skip that one because there is. So I'm going to skip the y equals 2/3 x plus 4. And the y, yeah. So there's a couple. Where are the examples I wanted? Yeah, there we go. Okay. So I feel like relatively clear what's happening so far. What I want to talk about are 2 other things when it comes to graphing lines. First of all, what if I wanted to graph y equal to 3? Well, I can find my y-intercept. So y-intercept, set x equal to 0. There's literally nowhere to plug in 0 for x. We get y equal to 3. Y is always equal to 3. And the x-intercept, there isn't one. If we set y equal, if we set y equal to 0, no, that doesn't work because our equation is y equal to 3. What we're getting at here, which I imagine many of you already know, is we have a horizontal line. Right? We have literally every point where y is equal to 3. There are an infinite number of such points, but some of the points are the points, say, 0, 3, and 1, 3, and 4, 3. But really, right, you can pick any point as long as the y coordinate's 3, and the x coordinate can be anything. So it's all the points that look like x comma 3, or x can be any number you want it to be, as long as the y coordinate is 3. So whenever you're graphing y equal to a number, you just get a horizontal line where all the y coordinates are that value. I should say all the coordinates have a y value of 3, and all the x coordinates can be whatever you want. In a similar way, if we were asked to graph something like x equal to -4, we would get a vertical line. So if I were going to graph x equal to -4, I would just get this vertical line where all the coordinates have an x coordinate of -4. So you got -4, 0, and -4, 1. And right there is -4 pi. Right, all the x coordinates are -4, and the y coordinates take on the range of every possible real number. So x equal to a number gives you a vertical line, y equal to a number gives you a horizontal line. Cool. So the other thing I want to talk about is, can you just go, oh yeah, sorry, that's so graphing lines typically feels easier in the slope intercept form, or as some people like to call it, the y equals mx plus b form. But doing it in the other form is also perfectly fine. So let's say we do something in the standard form. Ax plus by equal to c. What I really want to emphasize here is that to graph something in the standard form, you do not need to solve for y. Let's say we want to graph the following. 4x plus 3y equals 6. And I'm going to say, let me just write it out here. We do not need to solve for y. You might want to, that's perfectly fine, but it's not necessary. Because if we're graphing it, what do we need? 2 points. So we need 2 points. Specifically, you know what points I want? I want the x-axis and the y-axis, sorry, the x-intercept and the y-intercept. So to find the y-intercept, we're going to do what we always do. We're going to set x equal to 0. Okay, this is going to be a little more work. So I set x equal to 0. I'm going to get 4 times 0 plus 3 times y equal to 6. 4 times 0 is 0. So 3y equals 6, divide both sides by 3. You get y equal to 6 over 3, which is 2. Same idea for the x-intercept. For the x-intercept, we know that y has to be 0 because we're on the x-axis where y is 0. So we're going to set y equal to 0. So we'll call this like the cover-up method, where if I'm saying y equals 0, I just cover up within its y and then I solve for x equal to 6. Or if I'm solving for the y-intercept, I set x equals 0, just cover up for x and then I got 3y equals 6. I'm just going to plug it in. So I've got 4x plus 3 times 0 equals 6. You probably don't need to actually write that. You can be like, oh yeah, 4x equals 6. I know that 3 times 0 is 0. So 4x equals 6, x equals 6/4, and that reduces to 3 over 2. So my y-intercept is 2, my x-intercept is 3/2. I might actually draw this on with the marks because it's kind of, we can be precise here if we want. So 1, 2, 2, 2. So x is 3/2, which is 1.5 or 1.5, and the y value is 2. When we try our best to draw a line that goes through them, wow, that's not the straightest line I've ever drawn. Still not very straight, but better. That line is not very straight. You should drop that line that I've drawn. Now, I do want to mention, if someone asked you what the slope here was, it's not immediately obvious from anything we've done. So if you want to find the slope, the easiest way to find the slope is to solve for y, I think. There's a couple ways you can do it actually. So one way would be to solve for y. If I do solve for y, I get 3y equal to -4x plus 6. And then dividing both sides by 3, I get y equal to -4/3 x, and 6 divided by 3 is 2. So that would tell me the slope was -4/3. Or you could literally look at your graph and do a rise over run kind of thing. You could say, okay, James, rise over run. When I go from this point to this point, well, from left to right, the rise is actually -2 because you're going down 2. And the run is from 0 to 1.5 or from 0 to 3/2. So the run is 3/2. And then -2 divided by 3/2 is -2 times 2/3, which is -4/3. Usually it's a little easier this way if they're not fractions. This example is not as excellent as other examples could be. Well, what I do want to say here is that you can find the slope in a lot of different ways, but what I'm trying to get to, the mistake people often make is to say that the slope is just like the coefficient of x. The slope is not 4. The slope is not -4. The slope is the coefficient of x once you have isolated y on the other side. So if you have y equals something times x, then the coefficient of x is your slope. But if you have something like this, ax plus by equals c, the slope is not immediately obvious. There is a way to get it from here. I always forget what it is. It's like the negative a over b. That if you really want to be fancy, you can say the slope is negative capital A over capital B. But I never remember that. It's not the kind of thing I'm likely to remember. So I wouldn't recommend doing it that way unless you really like that. I don't particularly like that. I don't remember things like that usually. They just like, it's not a formula that sticks in my head. I would get the B and the A mixed up. I'm like, which one goes on top? Which one goes on the bottom? And I would probably want to do it the other way because we're used to thinking of like rise over run being y over x, but the coefficient of x actually goes on top of the right. So it feels kind of backwards. It's not the way I would do it. Let me give you one more example. Let's say I want to graph. Let's graph negative 10x plus 6y equal to 30. We're just going to graph it, and then afterwards we'll talk about the slope. This one, the slope is going to be a little nicer to find. So let's see, y-intercept. We're going to set x equal to 0. That's immediately going to lead us to that being not there. So we're going to get 6y equal to 30, which means we're going to get y equal to 30 divided by 6, which is 5. So our y-intercept is the 0.05. X-intercept. Same idea. So now I'm setting y equal to 0. I do want to emphasize, because I've seen people get this wrong so many times in life, when you're finding an intercept, you're always setting the other variable equal to 0. So when it's the y-intercept, you're setting x equal to 0. When it's the x-intercept, you're setting y equal to 0. It's always the other one, not the one you're trying to find the intercept for. When I do that, I get negative 10x equal to 30. Which means x is going to equal 30 over negative 10, which is negative 3. So negative 3, 0 is my my x-intercept. So negative 3, and I'm gonna, usually I would just kind of go, I'm actually gonna draw this one nicely, but I don't need you to draw it nicely. I just want to show you how you can see the slope. Oh, look at that, I actually went through the points I meant to go through. So there's the graph, and if the question was just to graph it, we would be done, right? We found the intercepts, we found 2 points, we found the intercepts, we drew the line between them. That's it, show's over. But if someone then asks you a follow-up question like, hey, what's the slope of this thing? Also, funny anecdote real quick. You know why we use the letter M for slope? Well, I can't think of the word now, but the reason we use M is because in French, the word for slope starts with an M. I really wish I remember what it was. And you know what the French use for their letter for slope? They use S. It's kind of neat. They use S, we use them because we're like, hey, we like your letters better than our letters. We like your words anyway. I thought that's kind of neat. So slope here, if I start here and I go there, my run is 3. And my rise is 5. So my rise over my run is 5 over 3. You could also do it a more, I don't know, this doesn't feel very normal to do it this way to me, but who wants to be normal? Normal is boring. Normal is also great sometimes. But right, we can also do it the more normal way and solve for y. So we could say 6y equals positive 10x plus 30, and then divide both sides by 6 to get y equals 10/6 x plus 30 over 6, which reduces to 5/3 x plus 5. And there's your slope if you want to do it that way. So if you're asked to find the slope, you can think about the rise over the run from your left intercept to your right intercept. Sometimes the left intercepts the x1. Sometimes the left intercepts the y1. Or you could do it the more conventional way of solving for y. Either way is fine. So again, graphing lines, not meant to be super challenging. I really, really, really encourage you to get used to just graphing them by finding the y-intercept and the x-intercept and drawing the line between them. And really not even worrying about any of this other stuff, right? Like I wouldn't draw those points normally. I would have just, if I was actually graphing this line, I would have done it as, I would have been like, all right, there's 5, there's about -3. Just, right? I don't even really want to make those marks before I do it. And then after I've drawn the line, then I would label the points. Okay, yeah, that's 0, 5. That's -3, 0. That's how I would really, really encourage you to draw your lines. Also, one last thing, do put arrows on either end, because we do need to indicate the line continues going in each direction forever and ever and ever. All right.